You all know I'm excited about nuclear fusion, don't you? Because of all the technology that's currently under development, this is the most likely one to dramatically change the world in the near future. It'd be clean and basically unlimited energy, so we could all stop pretending we'll go vegan. This is why I'm keeping a close eye on what's going on, and today I want to tell you about a very interesting new fusion startup in Germany. In the past decade, nuclear fusion startups have sprung up in many countries, but the vast majority of them are in the United States, which now counts more than 20. Europe is, as usual, far behind, and I was worried that Germany would miss the boat on that one entirely. So I'm happy about this new German startup. They called themselves Proxima Fusion, and the news is that they just received $20 million in funding to get on the way. Their approach is a spin-off from the Wendelstein 7X experiment in Greifswald, Germany. And since I know you're really just here because of my German accent, let's do this again. Wendelstein, Greifswald. Wendelstein 7X is what's called a stellarator, and the new startup wants to use a more sophisticated version of that, a quasi-isodynamic stellarator. That sounds super complicated, and it is, but the idea isn't so difficult to understand. The tried and trodden approach to nuclear fusion is using a tokamak. That's a hollow ring, basically, with strong magnetic fields. It's what the joint European Torus used and what ITER is supposed to use by the time it'll finish construction approximately in the year 4500. But in those tokamaks, the plasma tends to go unstable rather quickly, which is a huge problem. Not only do you not get the nuclear fusion, you can actually damage your machine. There's a smarter way to do this by using a somewhat more complicated shape with elaborate magnetic fields. This configuration is known as the stellarator, and the theory of it was developed already in the 1950s. The trouble is that back then they just couldn't solve the equations. It was only in the 1980s that the computing power had increased sufficiently to calculate what the magnets need to look like. So you see, the entire idea only became possible because of advances in an entirely different research area. And as we'll see in a moment, this is still the case. At the moment, Wendelstein 7X is the world's largest stellarator. It's about 5.5 meters in diameter and weighs a whopping 750 million tons. Its task is to test whether the magnetic confinement in the stellarator works as desired. You see here how this weird shape is built up from two layers of magnets. To generate sufficiently strong fields, the magnets need to be superconducting, so you have to cool them to a few degrees above absolute zero. Then you inject the fuel, and it follows this strange shape. Wendelstein was not built to generate energy from fusion, but just to show that they could keep the plasma stable. In contrast to a tokamak, a stellarator should be able to run continuously, and that in and of itself is bound to improve efficiency. So far, they've managed to keep the plasma stable for 8 minutes, which is really amazing. Their goal is 30 minutes. And they learned a lot of interesting things from this. For example, you might think that the nuclei in the fuel go around and around in the ring, and some of them do, but they can become trapped in parts of the ring and then they go back and forth, and their trajectories are usually small spirals. Okay, so the new startup now makes things even more complicated and even better by aiming at a magnetic field design that prevents the paths of the fuel particles from converging or expanding. Not only should this further improve stability, it should also decrease the heat loss from the plasma. And this is what the quasi-isodynamic thing is good for. That refers to a specific configuration of magnetic fields which have the same strength, that's the iso, on surfaces that wrap around the tunnel in which the fuel moves, that's the dynamic. The exact solutions for how this isodynamic field must look like are so complicated to calculate that no one knows how to do it. However, these guys who are doing the startup have figured out a way to do it approximately to high accuracy using artificial intelligence. So you could say that this is really a fusion of research areas. On their website, the company reports they have already begun working on the magnets and they're making good progress. Now, for what technology development and also funding is concerned, this startup is well behind the guys at First Light Fusion, which works on inertial confinement that we just talked about the other week. But to me, this ISO whatever stellarator thing sounds like a very promising path to pursue, though maybe they could come up with a more catchy name. If you ever want to annoy an astrophysicist, you just need to tell them that you don't believe in dark matter, because most of them are pretty much convinced that 80% of the matter in the universe is some invisible stuff that, try as they might, they can't detect. And that idea is more popular than ever because dark matter's biggest competitor, modified gravity, recently ran into trouble by making a wrong prediction. Or so I thought until I read this new paper. Let's have a look. The recent data that spelled trouble for modified gravity came from wide binary systems. Those are solar systems in which two stars orbit each other, but at a fairly large distance. I talked about this in several previous episodes. New is that John Moffat has shown that his theory of modified gravity fits the data just fine, so it seems somewhat premature to declare the idea dead. Why are the wide binaries such a problem for modified gravity? It's because if dark matter exists, which it may not, then the amount of this invisible stuff is very thinly distributed. You see, the reason that astrophysicists introduced dark matter was to explain some anomalies in their observations. Things like that galaxies rotate too fast and that galaxies and clusters move too fast. But this seems to happen only on scales much larger than our solar system. If you believe in dark matter, then the obvious explanation is that the dark stuff has a very low density. It adds up on large scales and then has a noticeable gravitational pull that speeds up galaxies. But in the solar system, you wouldn't notice it because it's just not enough of the stuff. And that dark matter would be so thinly distributed is also why you don't expect to see any evidence of it in these wide binary systems. In a binary system, basically what you see is what you get if you believe in dark matter. For modified gravity, the situation is more complicated because you can't just change the law of gravity in our solar system or on our planet. We'd have noticed that. So to make modified gravity work, you somehow need to switch it on for large things like galaxies. But how? The most widely used version of modified gravity is modified Newtonian dynamics, and in that approach, the modification kicks in at low acceleration. This means, loosely speaking, it becomes relevant once the average gravitational pull is sufficiently small. If you're near a heavy body like the Earth is next to the Sun, the average gravitational pull is large, so no modified gravity. But if you look at a star that's far away from the center of a galaxy, then the gravitational pull becomes quite weak because most of the mass of the galaxies is in the center. So that seems to explain why the effects kick in the outer parts of galaxies, just like observations say. The issue with wide binaries is now that the further away the two stars in the binary system are from each other, the lower the acceleration. So they cross over from the range where gravity should be unmodified to where it should be modified. And the data seem to say that there's no such crossover. For wide binaries, you have normal gravity, end of story. If that's correct, that's devastating news. I've actually worked on modified gravity myself, and for me this was definitely a point where I said to myself, that doesn't look good. And Albert agrees. I must add that there have been somewhat different results of the data analysis for wide binaries from different groups, and some of them actually say they do see what modified gravity predicts, but at least so far, it seems to me that the study that's using the most reliable data analysis clearly speaks against modified gravity. However, this per se isn't evidence of dark matter. It's just that it seems to remove the main competitor. At least that was the status so far. But, plot twist, maybe this data just paved the way for a different theory of modified gravity. You see, there isn't just one theory of modified gravity, just like there isn't just one theory of dark matter. The one that we most often talk about is modified Newtonian dynamics, MOND for short. It actually has a big shortcoming, which is that it is, as the name says, a modification of Newtonian dynamics, not of Einsteinian one. As such, it doesn't have a speed of light limit, so we already know that it can't be correct. However, John Moffat has a different theory of modified gravity, which is not Newtonian, and it works together nicely with Einstein's theories. He just calls it modified gravity, MOC, though I've heard people joking it really stands for Moffat gravity. This theory isn't new by any means. It's been around for about 20 years. It's just one of those cases where no one really cares. I'll admit that this is a bit awkward to talk about because I've known John for pretty much these 20 years, and I know he watches this channel. So, John, in case you're watching, I never understood why people aren't paying more attention to what you're saying. Yes, it might be wrong, but compared to a lot of other stuff I've seen, including my own, it works remarkably well. The major difference between MOND and MOC is that in MOC, the modification doesn't kick in with acceleration. It kicks in at a particular length, and how it kicks in depends on the type of system. In his new paper, John shows that in MOC, there just aren't any changes in wide binaries, no matter how wide. He's also previously shown that it works just fine for galaxy rotations, also for galaxy clusters, the cosmic microwave background, and what's there not to like? Well, one thing one could criticize, and I think that's one of the major obstacles, is that MOC is more difficult than MOND. It introduces two new fields, a scalar and a vector, and that makes the maths somewhat cumbersome. Really, the major difference to dark matter is that these fields don't have particles associated with them. So I guess that's why particle physicists don't like it. It's also a very interesting paper because should it turn out that the data later goes in favor of MOND after all, then John just killed his own model. So stay tuned. The other day, I read that using artificial intelligence creates fewer carbon emissions than human labor for creating images or writing text. Rubbish, I thought. But, well, let's have a look. On the face of it, the idea that artificial intelligence creates fewer carbon emissions than humans seems ridiculous. Carbon emissions are primarily caused by energy needs, either during operation or production. The human brain doesn't have much going for it, but besides being edible, it's famously energy efficient compared to a computer. A typical human brain runs on about 20 watts of power, though the average is much lower among politicians. A supercomputer uses more like 20 megawatts. That's 1,000,000 times more. Alright, most artificial intelligences today don't run on the biggest of the big supercomputers, but we just saw in an earlier episode that they eat up huge amounts of energy. If you use AI to do as much as generate an image from a text prompt, that takes up about as much power as charging your phone, in the ballpark of 3 watts, which is less than the 20 watts I just told you the human brain uses. Okay, let's look at what they did in this paper. They compared the emissions of carbon dioxide caused by using artificial intelligence and humans to produce text or images. For the AIs, they counted the training phase as well as the operation. So, say the energy that's eaten up when you ask Midjourney for a unicorn with sunglasses. On top of the power used during operation, they add a share of the total training emissions by dividing it through the expected lifetime query. For humans, they use the typical carbon intensity of living in different countries. From this, they then calculate the expected carbon emissions for the time that it takes the writer to produce a certain amount of text or a painter to paint a painting. They crunch the numbers and find that a typical US American needs about 100 to 1,000 times more carbon dioxide per page written or image produced. Wow, that's indeed a big difference. The exact numbers depend both on which AI model they use and where the human lives. They find, for example, that if you want to generate an image, then GPT is energetically quite wasteful compared to Midjourney. Then again, this isn't so surprising as it's just a bigger model. And if you outsource your tasks to India, that reduces the carbon footprint. Also not so surprising. I couldn't quite believe this, so I had a close look at the paper. To estimate the time, they used a self-evaluation from Mark Twain, who says that his output is about 300 words per hour. I just checked the length of this text and it's roughly 400 words, and it took me about 10 minutes to write, so maybe setting the quality level at Mark Twain might be putting the bar a little too high for the average internet content of today, but then again, that isn't going to make up for a factor of 100. What about the carbon emissions from producing the necessary hardware? They took this into account and also looked at possible later energy requirements for recycling. However, they say that these contributions are orders of magnitude smaller in carbon intensity than the training and operation. So basically, it doesn't make any difference. Okay, so science has spoken. AI is better than us. Well, not so fast. Data is all well and fine, but I'd like to carefully ask, what does it mean? Humans produce carbon dioxide emissions whether or not they write or paint. By giving the job to an AI, these emissions don't go away. They just add the AI on top. The reason human labor seems so carbon intensive is that a writer doesn't just write. A writer needs to keep its entire body alive, a body that's occasionally good for other things. An AI dedicated to a specific task doesn't have this entire overhead. I think a more sensible comparison would be to ask what's the difference in carbon intensity between a human who writes and a human who sits on a desk not writing. I suspect that the difference is so small as to be unmeasurable. That said, there's a bigger question behind this discussion, which is whether it's a good idea to invest into artificial intelligence if that'll increase carbon dioxide emissions. The answer depends on how much benefit you think will come out of it eventually. Personally, I think that energy demand is strongly tied to societal progress. The problem isn't the energy demand per se, but that at the moment the energy sources we use aren't environmentally sustainable. And of course, the reason that we use computers to take over certain tasks is to make space in our lives for doing something else, so that one day our video scripts will be entirely written by AI, and the footage of me speaking will be entirely produced by AI, and it'll be entirely watched by AI, and what was the point of that again? I was skeptical about electric vehicles until I learned that battery-powered cars accelerate faster. Since then, I've been convinced that electric vehicles are the future, obviously. But recently, I've changed my mind. I now think that hybrids are the future, obviously. This opinion shift was caused by a number of things. For one, the transition to electric vehicles will require a substantial extension of power grids globally. And of course, it's not done with the grid alone. Also, the energy has to come from somewhere. The estimated costs for this are staggering, and it's rather unclear how this will happen by the time that we're supposed to all be driving electric vehicles. In the European Union, for example, all new car sales are supposed to be electric by 2035. This isn't new. I went through the numbers in a long episode a year ago. What's new is that it's becoming increasingly clear that the transition isn't going as smoothly as hoped because many nations are simply not doing what's necessary. The International Energy Agency, IEA for short, warned very clearly in a recent report that the electric grid extension is the weak link in the energy transition. They say that to meet climate goals, the electric grid needs to be expanded at least 20% faster over the next decade than it did in the previous decade. The problem isn't just electric vehicles. The issue is also that renewable energy power plants need to be hooked up to the grid. According to the IEA, there are more than 3,000 gigawatts of renewable energy projects awaiting connections to the grid, with half of those projects in advanced stages. That's right, they're building renewable energy power plants, but we can't use them because they're not connected to the grid. They estimate that the United States needs to double their investment into grid upgrades to about 600 billion US dollar a year by 2030. In Europe, the numbers are pretty much identical. The European Commission estimates the necessary investments into the grid are 584 billion euros per year until 2030, about double that of 2021. Where's that money supposed to come from? Well, the European Commission says it'll come mostly from private sources, which sounds like a very well thought through plan indeed. What's the problem? According to McKinsey in the United States, the construction of new charging places for electric vehicles has picked up in the past years. But still, companies face obstacles because of missing personnel and partly because of missing hardware, such as specific types of transformers. It's basically a coordination problem. You can't just ramp up one sector of the economy on the snap of a finger. You'll need to also ramp up all sectors that supply it. In the EU, a big part of the problem is, guess what? Bureaucracy. For example, in Spain, the company Repsol built 1,600 charging stations in the past 2 years, but more than half still lack a power connection. That's because the company must get a license for the grid connection, and the responsible office is just extremely slow with doing the authorization process. A similar problem exists in Germany, Europe's biggest economy, where it can take months until a completed charging station is authorized and hooked up to the grid. In Germany in particular, the outlook for electric vehicle sales is bleak at the moment. It's because at the end of 2023, the government discontinued subsidies for electric vehicles, which has led to a major sales drop. And that isn't going to make companies more enthusiastic to build charging stations, and that in return won't encourage people to buy electric vehicles. By the way, if you remember, I had to buy a new car and was wondering if I should buy an electric one. I ended up buying a gasoline-powered one. Yes, I'm terrible. The major reason is that the town where we live has a total of one charging place and we don't own a house. And then I heard an advert for a Nissan car with the slogan, "Tank fuel, drive electric." And I thought, genius! You see, Nissan now offers a car, the Qashqai e-Power, that drives fully electrically, but the battery is charged by, wait for it, a combustion engine. It's not terribly energy efficient, and the car got some bad reviews because it actually eats up more fuel per mile than some cars that are powered just by combustion engines. But will it matter if people really buy electric because they like the acceleration? Finally, I think what tipped me over to hybrids is that all this talk about what to do with vehicles has made me realize just how good hydrocarbons are as energy carriers. Hydrogen, methane, ammonia is all really nasty stuff to deal with. But gasoline, wow, it smells good. So at the moment, my prediction is that this transition to electric will gradually be weakened in the next 5 years or so, as it becomes apparent that the grid extension isn't going anywhere near quickly enough, that renewables aren't coming by anywhere near fast enough, and that batteries aren't improving as quickly as they say. We'll still go mostly electric eventually, I think, because it's the most efficient option, but it'll take much longer than the plans say. You should bookmark this video so that in 5 years you can laugh about how wrong I was. Thanks for watching. See you tomorrow.